What does it actually mean for a machine to think? Not to answer, not to output words, to think. For years, the honest answer was, it doesn't. A large language model takes the text you've given it and asks one question over and over. Given everything so far, what's the single most likely next word? Pick it, append it, repeat. That's it. That's the whole loop. Watch what that looks like as a shape. Start at a single point, the prompt. Every word the model generates is one more step forward. One commitment, never revisited. No backtracking. No wait, let me reconsider. Just a straight line, marching left to right through possibility space, one token at a time, as fast as a matrix multiplication can go. That line is extraordinary at the things language is good at: grammar, style, retrieving a fact it's seen 1,000 times. But hand it a problem that actually requires multiple dependent steps, a logic puzzle, a proof, a 15-step arithmetic chain, and something breaks. Ask it a question where step 9 depends on getting step 3 exactly right. And a single greedy pass has no way to notice step 3 was wrong until it's 3 tokens deep into a step 9 that no longer makes sense. The model can't uncommit to word 12. Once word 40 reveals it was wrong, there's no mechanism to go back. The line hits a wall, and because it can never stop and revise, it just keeps going anyway, confidently, fluently wrong. So here's the idea that changes everything, and it's older than deep learning by decades. What if, instead of a single line, you let the model consider more than one continuation before committing to any of them? Not one path, many. At every decision point, branch. Try this word, try that word, try a third. Let each branch keep branching. What you get isn't a line anymore. It's a tree. Watch, one point, exploding outward into a fractal lattice of glowing possibility. Every branch a different way the reasoning could go, all of them alive at once, none of them committed to yet. That tree is enormous. At even modest depth, the number of paths through it outnumbers atoms in reach. You cannot explore all of it, and that, precisely, is the problem the rest of this video solves. How do you spend a finite asterisk amount of computation, searching an effectively infinite asterisk tree, and still walk away with the right answer? The answer is not a bigger model. The answer is a search algorithm, and it's going to take real math to get there. Psychologist Daniel Kahneman gave us a useful pair of names for this split, long before anyone was training transformers. System 1, fast, automatic, instinctive. The answer that's just asterisk there asterisk the moment you see the question. System 2, slow, effortful, deliberate. The kind of thinking where you pause, hold several possibilities in mind, weigh them, and only then commit. You use System 1 to read a stop sign. You use System 2 to do long division. Map that straight onto what we just saw, the single greedy line of token-by-token generation. Pure System 1, fast, cheap, one shot, no deliberation, which is exactly why it's brittle on anything that requires holding a plan together across many steps. The branching tree, generating multiple candidate continuations, comparing them, exploring before answering, that's System 2, implemented in silicon. This is the actual architectural shift behind every modern reasoning model. The single path doesn't get thrown away, it gets multiplied. Watch the line fracture. One thread becomes 2, 2 become 8, 8 become dozens, every one of them a live hypothesis about how the reasoning should continue, all growing at once. The model isn't smarter, word for word. It's the same next token predictor underneath. What changed is that it's now allowed to try asterisk many times before it has to answer once. For a decade, AI progress mostly meant one thing: bigger models, trained on more data for longer. That's still true, but starting around 2024, a second axis opened up, orthogonal to model size entirely. It's called test time compute. How much extra computation the model is allowed to spend asterisk after asterisk training. At the moment, it's actually answering your question. Let it branch, let it search, let it check its own work before it speaks. It turns out that spending more compute at inference time can buy you the same jump in capability as spending it on a vastly bigger model during training, sometimes more. But let it search the tree is not a free lunch. A branching factor of even 10, 20 layers deep produces more candidate paths than you could ever evaluate, let alone finish. The tree from scene 1 wasn't exaggerating, it grows that fast for real. Brute force System 2 thinking, explore everything, is just as impossible as it sounds, only slower and more expensive than System 1 mistake. You need a way to search asterisk smart asterisk. You need to spend your limited compute on the branches most likely to matter and abandon the rest early, ideally while still leaving room to be wrong about which ones those are. There's a 50-year-old algorithm, refined by decades of game-playing research, built exactly for that job. It's called Monte Carlo Tree Search. Monte Carlo Tree Search, MCTS, is the algorithm that let a computer beat the world champion at Go, a game with more legal positions than there are atoms in the observable universe. You cannot search that tree exhaustively, nothing can. Chess engines proved decades ago that clever brute force tops out fast. What MCTS does instead is beautifully pragmatic. It doesn't try to see the whole tree. It grows the tree, one small, cheap step at a time, always spending its next unit of computation where it's most likely to teach it something. 4 repeating phases. Let's build the tree together. Phase 1, selection. Start at the root, your current state, the question as asked. If this node already has children, branches you've explored before, don't pick randomly. Walk down the branch that looks most promising asterisk, so far asterisk. Using a confidence formula will open up completely in a few minutes. Keep walking down existing tree, child after child, until you fall off the edge of what's been explored, a leaf. Phase 2, expansion. You're standing at a leaf, a state the search hasn't grown past yet. Expansion adds exactly one new child. One concrete next step, one candidate move, one candidate reasoning fragment. The tree just got one node bigger. That new node has never been evaluated. It's an empty vessel, waiting to be filled. Phase 3, simulation, sometimes called the rollout. From that brand new node, get a quick, rough read on how good it is. Classically, that meant playing the rest of the game out randomly, all the way to a win or a loss, just to get some asterisk signal, however noisy. It's cheap and it's crude, but averaged over thousands of iterations, crude signals converge on the truth. In a few minutes, we'll replace this entire phase with something much smarter. But the job it does, a fast quality estimate for a brand new node, stays exactly the same. Phase 4, backpropagation. The result of that simulation doesn't just sit at the new leaf. It flows back up, updating every single ancestor on the path to the root. Each node keeps 2 numbers. How many times has this node been visited, and what's the running average value of the paths that passed through it? One iteration, and the whole spine of the tree updates its beliefs, a little wiser than it was a moment ago. Here's the picture to hold onto for the rest of this video. Think of computation itself as a glowing fluid. Every time you run these 4 phases, select, expand, simulate, backpropagate, you're pouring one unit of that fluid down through the tree, along the exact path you walked. It fills the nodes it touches. A node that's been visited often, and visited with good results, glows brighter. A node nobody has bothered exploring stays dim, almost invisible. Run the loop again, and again. Watch the tree light up unevenly, not uniformly, not randomly, but concentrated exactly where the search has found reasons to keep digging. This is the entire algorithm. There is no other machinery. Select down the brightest path, expand one new node, simulate a rough estimate, backpropagate it up, and repeat 1,000 times, 10,000 times, as much compute as you've budgeted for this single decision. Every iteration is cheap. The intelligence isn't in any one step. It's in the asterisk shape asterisk the tree grows into after enough of them. A structure that has, without ever checking every possibility, concentrated almost all of its attention on the small number of branches actually worth having explored. Let's slow down and actually watch 4 iterations happen, one at a time. Iteration 1. The tree is just a root with 2 or 3 untried children. Selection has nothing to compare yet, so it picks arbitrarily. Expansion adds a node. Simulation gives it a mediocre score. Backpropagation writes that score into the root. Iteration 2. Now one child has data and the others don't. The untried ones carry that huge exploration bonus will formalize shortly, so selection tries a different branch this time, on principle. Iteration 3. A branch that scored well gets revisited. Expansion pushes one level deeper for the first time, and the fluid starts pooling along one particular path more than the others. Iteration 4. That path gets selected again, deepened again. You can already see which branch of the tree is pulling ahead, not because we told it to, but because good results earned it more visits, and more visits earned it even more attention. This is the loop, compounding. 4 phases, 1 repeating loop, 1 flowing resource. Selection finds where to spend the next unit of compute. Expansion grows the tree by exactly 1 node. Simulation gives that node a first, rough opinion. Backpropagation makes sure that opinion is remembered everywhere it's relevant. The only piece we've left deliberately vague is selection's confidence formula. How, exactly, do you decide which branch looks most promising so far? That formula is the difference between a search that's smart and one that's just lucky. Before we get there, we need to fix simulation's biggest weakness, because a random rollout is a terrible way to judge a half-finished thought. Random rollouts worked for Go because a game of Go always ends cleanly. In a win or a loss, noisy signal is still real signal if you average enough of it. Reasoning and language doesn't have that luxury. You can't randomly finish a half-written mathematical proof and get a meaningful right or wrong. Playing every candidate path out to completion for every single node would be catastrophically expensive. You'd burn your entire compute budget just generating filler text you throw away. The fix, pioneered in game-playing systems like AlphaGo and perfected in AlphaZero, is almost audacious in its simplicity. Don't simulate to the end. Train a neural network to just look at a partial position, a half-built board, a half-written reasoning chain, and estimate directly how good it is. No playout required. 1 forward pass through a network, and you get a number. Formally, we're approximating a value function. Given a state S, we want V, S. The expected outcome if play continues from here under optimal strategy. We can't compute that exactly. It would require solving the entire remaining game tree. So instead we learn a neural network with parameters theta that approximates it. V theta of S, trained on millions of past positions until its estimate tracks the true value closely enough to be useful. Alongside it, a second output, a policy, P of S, a probability distribution over which next moves are even worth considering, so expansion doesn't have to try all of them either. Picture the network as a handful of layers, dense with connections, sitting just outside the tree. A brand new node, freshly expanded, still dim, gets piped into it. 1 forward pass later, out comes a scalar. A value estimate, somewhere between this is almost certainly a dead end, and this is extremely promising. That number becomes the node's brightness. No rollout, no simulated game, just a trained sense of quality, applied instantly at every single node the search touches. The direct descendant of this idea in language model reasoning is called a process reward model, or more casually, a verifier. Instead of only grading a final answer, a verifier scores each intermediate reasoning step *. This line of the proof looks sound, that one looks shaky, which is exactly the per node value signal Monte Carlo Tree Search needs to decide, cheaply and instantly, where its next unit of compute is best spent. Where does a network like this actually come from? The same place most learned judgment does, labeled experience at scale. AlphaZero trained its value network purely from self-play, millions of games against itself. Each final win or loss retroactively labeling every position that led there. Language model verifiers learn from a similar trick. Generate many candidate reasoning chains, check which ones landed on the right final answer, and use that outcome to label every intermediate step along the way. Sound reasoning that led somewhere correct gets reinforced, shaky reasoning that led nowhere gets pushed down. The network never needs a human to hand label, step 4 looks suspicious. It learns the pattern of what good reasoning looks like from which reasoning chains actually worked. So every node in the tree now has an estimated value, updated every time the fluid flows through it. That still leaves the one question we deferred all the way back in selection. Given several sibling branches, each with its own visit count and its own average value, which one gets the next unit of compute? There's a genuine tension here. Exploitation says, go back to the branch that's already scored well, don't waste compute double-checking a sure thing. Exploration says, that branch has barely been visited. its high score might just be noise, and you won't know until you check. The formula that balances the two is called UCB1, the upper confidence bound. For a node I, its score is x bar I plus c times the square root of log n over ni. Read it in two pieces. X bar I is pure exploitation, the average value this branch has earned so far. Higher is better. The second term is pure exploration. N is how many times the asterisk parent asterisk has been visited total. Ni is how many of those went to asterisk this asterisk child specifically. When Ni is small, this branch is unexplored. That fraction is huge, the square root is huge, and the exploration bonus dominates, pulling the search toward branches it doesn't understand yet. As Ni grows, that bonus shrinks toward 0, and the score converges on the honest average. C is just a dial, controlling how curious the search is willing to be. Let's make it concrete with actual numbers. Say the parent has been visited n equals 100 times total. Branch A has been visited 80 times, with an average value of 0.7, a strong, well-established track record. Branch B has been visited only 5 times, with an average value of 0.5, mediocre, but barely tested. Exploitation alone would tell you. Pick A, obviously, 0.7 beats 0.5, but run the exploration term. For branch A, log of 100 over 80 is small. The bonus barely nudges its score. For branch B, log of 100 over 5 is much larger. Its exploration bonus can be big enough to lift its total score above branch A's, even though its raw average is worse. UCB1 sends the next unit of compute to B, not out of naivety, but because 5 visits is not enough evidence to write branch B off, and the formula knows it. Watch 4 sibling branches compete under this rule, on a loop. Early on, the barely visited branches get a flattering exploration bonus and pull ahead in score, even though their true value is unknown. The search sends compute their way almost on principle. As visits accumulate, that artificial boost decays, the noise washes out, and the branches that genuinely have the highest value settle into the lead, honestly, on merit. The formula doesn't need to be told which branches are good. Given enough iterations, it finds out on its own, and it never permanently commits to a wrong answer early, because every branch, no matter how bad it looks, keeps earning a small exploration bonus for as long as it's undervisited. Here's the payoff. Once a branch has been visited enough times that it's confidence bound, its best case score, exploration bonus included, can no longer catch up to the current leader. There is no reason to spend another drop of compute on it. It's mathematically dominated. Watch it. The losing branches don't just fade quietly. They get marked, flare red, and collapse out of the active search entirely. That's pruning, and it's the other half of why this algorithm works. It's not just deciding where asterisk to asterisk look. It's proving, rigorously, where it can stop looking. And that's the whole loop closed. Compute is finite. You fixed a budget before you started. 1,000 iterations, 1,000,000, whatever you can afford. Every iteration pours a little more of that fluid into the tree, concentrated by selection's exploration bonus, evaluated instantly by the value network, pruned the moment a branch is provably behind. When the fluid runs out, when the budget hits 0, the search simply stops, and you read the answer straight off the tree. Whichever branch off the root was visited the most. Not the branch with one lucky high score. The branch the entire search, collectively, spent the most of its compute standing on. Let's stand back and look at the whole shape of what we just built. Instead of one greedy line of tokens, a tree of possibilities. Instead of exploring it blindly, 4 repeating phases, select, expand, simulate, backpropagate, that grow the tree exactly where it's useful. Instead of a crude random rollout, a trained value network that judges a half-finished thought instantly. And instead of exploring forever, a precise formula, exploitation plus an exploration bonus, that knows exactly when a branch has proven itself unworthy of more attention. 4 ideas, 1 search, and here's what makes this worth 30 minutes of your attention. This is not a niche trick for one problem. This exact skeleton, search a tree of possibilities, guided by a learned value, budgeted by a compute limit, pruned by an exploration rule, is what took Go from unsolvable by computers to superhuman in under 2 years. It's the architecture underneath the reasoning models that now sit with problems for minutes before answering, checking their own steps the way you'd check your own long division. It's the same loop, one level up, inside agents that plan a sequence of tool calls, weighing which action to try next. Different skins, identical mathematical skeleton. So pull the camera back. This single tree, glowing brightest along the paths worth remembering, it's just one search. Right now, at this exact moment, there are millions of others. Other prompts, other models, other agents, each one growing its own tree, spending its own budget of compute, pruning its own dead ends, all completely independent, all running the same four-phase loop underneath. Watch this one tree shrink and shrink until it's a single point of light, and around it, more points and more, spreading outward into a field that looks unmistakably like a galaxy. Maybe that's the honest way to describe what thinking has become in these systems. Not a single bigger function, computed once and delivered, but a search, a finite amount of a precious resource, spent wisely, down a tree of what might be true, what might work, what might be the right next step, guided the whole way by a sense, learned from experience, of which branches deserve the light. Whether that's a fair description of what happens in your own head when you pause before answering a hard question, that's a longer conversation. But for the machines, right now, the math is exactly this. A tree, a fluid, a budget, and the discipline to stop pouring the moment it runs out. That's the math of reasoning. Thank you for thinking it through with us.